Hello everyone, my name is Hygate and I'm a postdoc at Allegro who started last year in March. And today I'm going to be talking to you about how you can analyze your ALMA data after you have calibrated and imaged it. So once you've completed calibration and imaging, you will have a data cube. The data cube is a three-dimensional data product with two spatial dimensions, right ascension and declination, and one velocity dimension. And we will look at a few data cube analysis methods that you can use to further understand your data cube. We will look at analysis using CASA and also how to make movies in DS9, and you can download them from these links. Many other tools are available, and indeed we have many of these available on our computer facilities. Just contact us if you want to use them, and with any other questions or requests or assistance with analysing your ALMA data. And in addition, you can create your own bespoke analysis tools, of course. So the analysis techniques that we're going to be looking at today involve reducing the dimensionality of your data cube from 3 dimensions down to 1 or 2 dimensions to allow you to get a more intuitive feel for the data and better understand them. So listed here, we have a number of different analysis methods. Firstly, spectral profiles. These are one-dimensional slices along the velocity axis. Channel maps, two-dimensional slices along the velocity axis. Movies. These are a series of two-dimensional velocity slices along the velocity axis. And moment maps, which are essentially some sort of integration along the velocity axis. And finally, we have position velocity plots, which are slices along the spatial dimension. So spectral profiles are simply one-dimensional slices along the velocity axis, as I've said, and they can be easily created within the CASA viewer. So you can see an example here where we have the emission from a source measured in millijanskis per beam plotted against the radial velocity in kilometers a second. The first thing that you need to do is open the CASA viewer. You can do this using the command InView in CASA, and this works equally well with CASA images and FITS files. Once you've opened the CASA viewer, then you want to select the ellipse tool there and click and drag it around your source, like so. Once you've done that, you can simply go up here to the spectral processing tool, spectral profile tool, and open up, and then you will have a spectrum created for that source. Now, channel maps are 2D slices along the velocity axis. So these are much like a normal image you would get from, say, an optical telescope, in that they just give you information about the emission in a particular region of space. However, they're only for one particular slice in velocity space. And again, we can create these in the CASA viewer. So just open the CASA viewer as normal in view, and then you can slide the image here to the channel that you're interested in. And once you've selected that channel, you can simply go in here into the data display options and customize the look of your image. The most important thing here is color wedge, so that we can have scientifically useful information. So if you select that you want to display the color wedge, then you can see that you have a scale on the image. Then simply print the image, and you want to select here to save it as a PNG image and not a PDF, so that you can have it in color. For some reason, PDFs will come out in color in black and white. Now just give it a name. In this case, I call it channel map, and then save, and then you have your completed channel map. Okay, now movies are basically a series of channel maps that are displayed in order of their velocity. So again, we can just view one of these in the CASA viewer by opening InView, and just as before when we were able to scroll through manually, we can press play and scroll through. using these commands here. You can see step through individually or play. However, you might want to save out one of these movies in order to use in the presentation. So here you can see a movie that I've created using DS9, and from the command line you can just type DS9, the name of your image, as a FITS file in this case, not an ALMA image, and then you can use a number of different commands here. So you can give it a color map to make it look nice, set the scale limits between minimum and maximum. If you don't do this, DS9 will treat each channel individually, and the scale will not be consistent between them. Now we give it the movie command. Slice is how DS9 refers to these channels, so you're just going through all the slices of channels, and then you want to save it as a GIF, as a GIF is higher quality than the alternative MPEG format. If this fails, you'll need to update DS9, as these options are only available in the most latest versions of DS9, or if you're willing to have a worse looking map, you can try an older color map, for example BB, and use the MPEG format. Now we come to the topic of moments. Moments are basically a way of integrating your spectral line in velocity space to learn more about it, and they allow us to characterize the spectral line. So there are a whole load of moments ranging from 1 to 11 that are accessible using the InMoments command in CASA, and you can see a description of them here. And many of these are useful and interesting, but for the moment we're just going to focus on the 3 most commonly used moments. The 0th moment, or the integrated value of the spectrum, the first moment, which is an intensity-weighted coordinate that's used for velocity fields, and the second moment, that's the intensity-weighted dispersion of the coordinate used for velocity dispersion fields. So if we look at our spectral line here, you can see that it has a distribution of flux in velocity space. Now we can use the InMoments task in CASA to analyze this, and to note that generally it's recommended that you use no threshold in terms of signal for moment 0, but to get meaningful information from moment 1 or higher map, you will need to exclude noise with some kind of threshold, and I'll explain how to do that in the following slides. So moment 0, the integrated flux, is exactly what it says. Basically you just integrate all of the flux that's within that line. This is useful, for example, for finding out the total intensity of a line or the total gas mass in an image or something like that. And you can see we can create this very easily using the InMoments task in CASA. We just need to specify the spectral axis. This is the velocity axis, the axis we want to integrate over here. Give an image name, tell it that you want the 0th moment here, and give some out file that you will save it as. And as I said, normally no threshold is needed for a moment 0 map. And indeed, it's often advised to avoid it so that you don't bias your moment 0 map. And you can see here's an example of the data cube I was showing before, but now as a moment 0 map. And then if we look at moment 1, this is normally used as the velocity, and what you get from here is the intensity-weighted velocity of the line, and this is used to tell you at what place in velocity space this line is sitting, and is used to get a velocity field of your image, essentially. And so again, we specify we want to integrate over the spectral axis, but this time differently. Of course, we specify that we want the first moment. We can also use the include pix command, and we specify a minimum and a maximum pixel value that we want to integrate over. And so in this case, I've chosen the lowest value that I'll accept is 3 times the sigma value in the image, and the highest is the maximum pixel value in the image. But again, you need to choose these accordingly based on your image and the size you want to achieve. You can see here a velocity profile of the data cube that we've been looking at so far, and how the velocity differs from one side of the image to the other in different regions. And then the final moment that we're going to go into detail here today is the second moment, and this is usually used as a velocity dispersion measurement to get a velocity dispersion field of your image. And we do exactly the same as for the first moment, except this time we specify the second moment here in the call to in moments. And again, we're using include pics for thresholding as before. And you can see now the velocity dispersion field and how our velocity dispersion peaks in this region that is probably outflowing, as would be expected. Now, the final type of analysis method that we're going to look at is the position velocity diagram. Again, you can just open the CASA viewer using the InView command and create it directly from there. So here we want to click on the position velocity tool at the right-hand side of this bar. Again, we just draw on the image directly. In this case, we draw a slice through the image where we'll be extracting the position velocity information from, and afterwards we can click and drag. We then go to the right-hand side and select the PV section in the region dialog box and click Generate PV to generate our position velocity diagram. And then CASA displays a position velocity diagram here for us. And you can see the offset from the center in arc seconds against the radial velocity, sorry. Now, the position velocity diagram can be used to understand more about the velocity structure of the image. So, for example, for creating something like a galaxy rotation curve. And here's a list of resources, and all of the links in this file will be available when you download the file from our website. Links will be sent to you by email after the after the end of the session. And there's the CASA documentation, which has all the details about how to use CASA. CASA guides, which give you a more sort of step-by-step example of how one can do imaging analysis in CASA. The CASA cookbook, which has a huge amount of detail about CASA. If you want to know more about it, you can go there. And you can download CASA DS9 from the links you can see there. There are also a number of analysis tools that have been developed by the EU ARC node, which will be useful for your science. You can find this link. And as I said before, Allegro maintains a number of analysis tools on our computers. And we have in-house knowledge of a number of analysis tools that might be useful for you in your science. So, as always, don't hesitate to contact us at alma@strw.lightuniv.nl with questions or requests for assistance with your ALMA data. Thank you for listening, and I'll now take any questions that you may have.